Good day, guys. I'm going to discuss with you another application of definite integrals, and this is about volumes of solids of revolution by integration. So, volumes of solids of revolution by integration. First, what is solid of revolution? So when you say solid of revolution, it is a solid generated or formed by revolving a plane about a line in its plane. And this line is called an axis of revolution. And sometimes it's a special case, axis of rotation. For instance, if I have this plane region, let's say my plane region is a rectangle attached, for instance, to this line, vertical line, and above this horizontal line. If this is my region, and I'm going to rotate it about this line, what is the solid formed? Or solid of revolution. So once I rotate this about this vertical line, this region, which is a rectangle, this is what I will generate. No? I will generate what? Guys, a cylinder, no? In particular, right circular cylinder. Okay, guys? Correct, guys? So, again, once you revolve this region about this vertical line, this is what you will able to generate. A right circular cylinder. Okay? What about if you have, let's say, a semicircle? What do you think the solid that will be generated once it is revolved about its diameter? Guys, so let's say this time I have a semicircle. Let's say this is my region, and assume that this is a semicircle of radius r. If you are going to revolve it or rotate it about this line, what do you think will be formed, guys? Sphere, no? A trace here. Okay. Not easy to make this. So this is now the sphere. So this is semicircle. And then this is the sphere. Favorite of whose celebrity? This shape, his or her favorite. Rod Domingo. Who do you think? Si Britney, no? Britney Spears. So that is her favorite shape. Okay, guys? What about if, let's say, a right triangle formed with this horizontal and vertical lines is revolved or rotated, no? About, let's say, one of its legs. For instance, let's say this is my triangle. If I'm going to rotate this region about this vertical line, I will able to generate, what do you think will be generated? Conical shape, no? So this is what we're going to generate. So a right circular cone, no? We now have this right circular cone. Okay, so that's what we mean by solids of revolution. But these solids of revolutions that we formed out of these regular shapes are regular solids, no? Their volumes can be determined by our formulas in geometry. So we have a regular formulas for the following solids. For instance, if you want to get the volume of this right circular cone, all you have to do is to find the radius and what? And the height. Okay? And then multiply by 1/3 pi. Okay, 1/3 pi, then square the radius times the height. So let's say this is the height and this is the radius. Now for the sphere, if you know the radius, for instance, if this is the radius, so the volume is given by what, guys? What's the volume? 4/3 pi r cubed. Whereas for right circular cylinder, we have pi r squared times the height. Okay, guys? So if this is the height and this is the radius, so this is the volume. Now our concern is on the solids of revolutions formed out of irregular plane regions. So that's the role of definite integral, no? To compute for the volumes of solids of revolutions formed by the regions that are not regular. Okay? So there are three methods of computing volumes of solids of revolution. Number one, we have what we call circular disk method. Have you seen a circular disk, guys? Definitely yes, no? It is the shape of normally a coin. Okay? If you are going to look at our coin, so that is a circular disk. So when do we use this method, guys? This method is used whenever the plane to be revolved about the axis of revolution so again, when I say AOR, I mean axis of revolution or axis of rotation. Okay, guys? AOR. has a straight side, fully attached, or coinciding to the axis of revolution. Okay, guys? And the volume element that you will able to form, so instead of area element, we will be talking about volume element. And when the area element is revolved, you will able to form what we call circular disk here. The volume element, meaning the circular disk, for this case, is perpendicular to the axis of revolution. Okay, guys? So again, this method is used whenever the plane to be revolved about the axis of rotation has a straight line or straight side fully attached to the or coinciding to the axis of revolution. Okay, guys? And then the volume element is perpendicular to the axis of revolution. So let's illustrate that. So let's say this is my lines. So let's say this is my region. And I want to revolve this about this horizontal line. And of course, you can do it in a vertical line, of course, depending on the region, okay? If I'm going to revolve this irregular region about this line, we will able to form using circular disk method. So we have to draw the volume element, and the appropriate here is, for this case, vertical. Okay? So let's say this is my area element. When it is revolved, it will become a volume element in the form of circular disk. Once I rotate it about this horizontal line, I will able to generate, let me copy this. So that I will able to form the desired volume or the desired solid of revolution. So I'm going to rotate this. So I think I need to flip this. I need this one, this part, and this together with this one. Copy, and then flip. Let's flip this vertical. Okay, so let's have now, let's assemble. So we have this solid. Oh, can you imagine, guys, the solid form? Ayan. So this is approximate shape. This is the reflection. And this is what we have. So when rotated, you will able to form like this. Okay, guys? So of course, this is supposed to be, let me erase that part. This one, no need for this. Okay? So that is the solid generated. And this is the original area that we had. I think let me have thin only. So this is the original region. Okay. And that is the solid that is formed after revolving about that line. Is that clear, guys? So, and the disk, of course, that is formed will be looking like this. So this is how it looks like. I will able to form a disk. So this shape, this is approximate shape of the disk. Can you imagine the disk, guys? So this is the disk. If you're going to position it horizontally with face horizontal surface, so it will become a disk, like the shape of your, let's say, a coin, no? 5 peso coin. Element here, volume element is vertical, or using vertical element. So that you have area element vertical. When rotated, you now form a volume element that is a vertical circular disk. If I'm going to flip this, here we go. Yeah, and I want it to be like this. If you have this shape, let's say this is your shape, this is the corresponding solid. This time you have horizontal, no? So I'm going to flip this also. Is that correct? So that's one. So it's like a cup, no? So this is a solid that is formed if you rotate that or revolve about this vertical line. And you use horizontal element this time. Horizontal element. So in this case, this is our dt, and dt here happens to be dx. And if your element is horizontal, your dt is dy. Okay? So, and the radius of this volume element, so this is the volume element. The volume element is given by what? So let's draw. So we have this disk, no? Okay. It's hard to draw the disk. Let me have it here. So this is the half and another half. So this is the disk. This is the one that is used to approximate the volume. So instead of covering the solid by, the area by rectangle, for the solid, we cover this by what? By this disk. Okay? Yeah. So this has dimensions. What are the dimensions? Radius, and then the thickness is dt. If it is horizontal, dy. If it is vertical, the dt is dx. And the volume element is represented by differential of b, and this is equal to, since this is a cylinder, pi r squared, then times the height, and the height is dt. So that the volume is given by what? Integral from a to b. So the volume runs from what? So we take it from the original area. So the area runs from, for instance, if vertical, from this A to B, if horizontal, from A to B, here. And that will be the limits for the volume, no? Pi, I can put that out because that is a constant. R squared dt, where R is either x right minus x left, or y higher minus y lower. So if you use horizontal element, okay? if you use vertical element, y higher minus y lower, the radius. And the dt, of course, either dy if horizontal element, dx if vertical element. Okay, guys? Yeah. So that is how to use this circular disk method. This is the formula of finding the volume of this solid. So let us have a particular example. Find the volume of the solid generated when the area bounded by the given curves is revolved about the indicated axis. Let's say our curves involved, we have x equals square root of y, x equals 0, and y equals 3. And I want to revolve this about the line y-axis. And y-axis is the line x equals 0. Okay? So again, this is x equals 0. So first, we're going to trace the region. So what's the region, guys? So we begin by the points of intersection. So we have x equals square root of y. We want it to be to meet x equals 0. Let's see if it will meet x equals 0. If x is 0, we have 0 equals square root of y. Therefore, y is 0, no? So it means we have a point 0, 0. And then if y equals 3, so we have x equals square root of 3. So therefore, I mean y equals 3, therefore x is square root of 3. Okay? So hence, we have a point 3, square root of 3, 3. Okay, guys? Guys, so let's now trace. By the way, x equals square root of y. When we square, this is x squared equals y. This is a parabola, but part only. Okay? So because the original is x equals square root of y. Vertex at 0, 0, and this parabola opens upward. But we want only the one that is in the first quadrant, okay? So let's now trace the region. I'm just going to have it freehand, no? Because it will take much of our time if I'm going to have it perfect straight line. We have 1, 2, 3. Square root of 3 is around what, guys? 1.7. So this is somewhere here, 1.73. So I'm going to count along the y1, 2, 3. So this is the line y equals 3. So that's the line y equals 3, bounded by this. And then the parabola that opens upward with vertex here, 0, 0, opening upward. When x is 1, y is 1. Okay? So we have 1 here. 1, 1. So, and the parabola has to intersect the line y equals 3 here at x equals 1.7, 3. Okay, guys? So, somewhere here. Almost 2, no? So, this is 1, and this is 2. This is 1, 2. This is the line y equals 3. So the parabola opening upward, we get this parabola. Okay. So this is the region bounded by the y-axis. So this is y-axis. X equals 0 is y-axis. This parabola that opens upward, so that is a parabola opening upward. So, but we do not want this part, no? We only want this region. And above by what? By the line y equals 3. Okay? So if I'm going to revolve it about the line x equals 0, that is about the y-axis. So this is where I'm going to revolve it, guys. We will able to form a solid, no? So this is the solid that we will able to form. Make it smaller, no? So that I'll just make it smaller, just to show the solid form. So this is the solid form. If I'm going to continue the pink, 1, I'm going to just have the white, no? Let's have just the white. Just to show you how the solid looks like. Okay, so we have the x-axis 1, and then here 2. So intersected here, somewhere there, negative 1.713 because reflection. So this is the reflection on this side. Okay, and this is the solid that we will able to form. Okay, guys, and that's the solid. And the appropriate element, because you want circular disc, is circular disc possible? Now, to form a circular disc, we need the element perpendicular to the axis of revolution. Is horizontal line possible? Because that is the one that is perpendicular, guys. Is it possible, guys? Possible, no? We can make use of that, okay? So this is the element. Yeah. So just add freehand. So the thickness this time, our dt is what? dy, no? So this is dy, our dt. And this is the radius. And this one is the radius. When revolved, it will form what we call disk. So it will be somewhere here. So let's say this is the disk that we form. Okay, so that's the disk. Is that clear, guys? And so that's the solid. So how to form the volume? Volume is equal to pi integral from A to B radius squared dt. Okay? So our R here is, for this case, x right minus x left, because this is horizontal. Our x right is the curve. Y equals what? X squared, or x equals square root of y. So this is x right. X left happens to be 0. Okay? So that is square root of y minus 0. So giving square root of y. And then our dt is dy. Hence, volume is given by the original region runs from, that is to be revolved, runs from 0 to 3. We look at the y values because this is what? Horizontal element, no? And we use what? What is the volume element that is formed? Circular disc. So we now use circular disc method, CDM. Okay? So pi integral from 0 to 3, y values from 0 to highest value of y, 3. Then square root of y, that is our radius, square it. And then dy, that is our dt. So giving pi integral from 0 to 3 of y dy. And this is equal to what? Pi, what is the integral? That is y squared over 2, evaluated from 0 to 3. So getting pi multiplied 2. So what's the value of this? Or what is square? 9 over 2. Okay. So what's the volume? Okay, guys. So again, if you're planning to use circular disc method, be sure your element is perpendicular to the axis of revolution. And it should be what? Appropriate. Let's say you want it to be perpendicular to the axis of revolution, but unfortunately, it's not an appropriate element. But the appropriate, for instance, is the one that is parallel. There is another method for that. So do not force to use circular disc. If not, appropriate the element that you are going to form. Okay, guys? And be sure manageable to you to solve the, let's say, y in terms of x or x in terms of y, whatever is the requirement for that element. Remember, for vertical element, you must be able to express y in terms of x and x in terms of y if you use horizontal. Okay, so let's have another one. Let's say I have y equals e to the x times 2 here, then minus 1. X equals 0, and the line y equals 3. And then axis of revolution to be revolved about y equals 3. Okay? So again, we are going to start with the points of intersection to be able to sketch the region. Our main curve involves exponential function y equals 2 e to the x minus 1. If x is 0, we have y equals 2 e to the 0 minus 1. The value of y is 1. Hence, we have a point what? 0, 1. Okay, guys? What about if y is equal to 3? So this is 3 equals to e to the x minus 1. 2 e to the x equals 4, no? So e to the x is equal to 2. So hence, we have x is equal to ln 2. If you take the ln of each side, we have x equals ln 2. Hence, our point is ln 2, 3. ln 2 is approximately what? So that is 0.69 or almost 0.7. No? Yeah. So that's the point. Okay? So no more. So we are now ready to sketch the region. So let's have the region now. I think I can have it here. Okay? Yeah. So this is the y. And then we have maximum y3, 1, 2, 3. So let's have up to here, 3. And then along x, we have 0.69, no? ln 2.69. Let us have larger scale here. 1, 2 to magnify the figure. 1.60, 0.69 is somewhere here. 0.69, I think. I think I need to make it uh, larger. Let me have it here. So let's say this is my 1. 0.7, this is 0.5, 0.75. So somewhere here is the 0.7. Intersected where? At 3, no? When x is 0.5, 2 times shift ln 0.5 equals minus 1. That is at 2.29. 0.5, 2.29. So it's here. Okay? Now what about the region, guys? Okay. Yan. It is asymptotic, I think, to this x-axis. But we do not want that, no? This is what we want. This region bounded by the y-axis. The line y equals 3. So this is the line y equals 3. So here. So this is the region. Okay, guys? So this is the ln. What is this blue, guys? This blue is y equals 2 e to the x minus 1. And this blue, a yellow, y equals 3. Okay? And then this is, of course, x equals 0. So this is the region. Yan. So if you're going to revolve it about the line, what is our axis of revolution? Y equals 3. So about this yellow, I'm going to extend this. This is where we're going to revolve it. About here. Okay, guys? So 1, 2, 3. So assuming this is the point, yan, where they will meet. So this is the approximate shape. Okay. This shape. When revolve about this line, so you will generate another like this. 1, 2. So 1, we count to 1, 1, 2. So up to this. So this is where the reflection here. Okay. So we now have like this. Can you imagine now the shape, guys? What's the shape? Yeah. So this is the shape of the solid. Okay, guys? That's the shape. It's like a cup, no, again, but lying, the surface is vertical. So that's the volume. So using what's the appropriate one? So possible you can actually solve it using horizontal. You can also have it vertical, but we want a circular disc. So let's try if perpendicular to this axis of revolution is possible. What is that, guys? Vertical this time, no? The one that is perpendicular. Okay? So using what? Using vertical element. Yeah. Meaning, we are going to use what method? Circular disc method. Because that is perpendicular. Okay? When this is revolved, so this is the reflection, we will generate a disc. Okay? Yeah, that's the disc. Okay. So the volume, therefore, is given by pi integral from a to b radius squared dt. And this is equal to pi integral. What is our radius? Y higher this time minus y lower. Because our dt is what? Our dt is dx because that is vertical. And then y higher happens to be the line y equals 3. So y higher is 3 minus y lower, that is This one, no, this is y lower, that blue, and this the one that is y higher, y equals 3. So the blue one is 2 e to the x minus 1. Simplifying, we get 4 minus 2 e to the x. Right, guys? What now do we have? Limits. The limits runs from 0 to ln. What is this, guys? This point. That point is ln 2. From 0 to ln 2. We use x values, no? Because this is vertical, running from leftmost x value to rightmost x value, the region that is to be revolved. About the line y equals what? This line equals y equals 3, no? So again, the limits, we get it from the original area to be revolved. So radius, our radius is 4 minus 2 e to the x, quantity squared dx. Okay? So let's have here. So this is pi. Oh, how do we evaluate the integral of this, guys? We expand, no? 16 minus 16 e to the x plus 4 e to the 2x, quantity dx. And that is equal to pi. Or what is the integral? 16x minus integral ng e to the u du. So that our u is x. So that is e to the u times 16. So we have 16 e to the x, no? Plus 4 times our u here. So here our u is what? 2x. And then du is what, guys? What is du? 2 dx. So I need to put 2 balanced by 1/2. So put 2 balanced by 1/2. It will now be 2. 4 divided by 2. And then times 2 here. So e to the u du now after multiplying by 2. So we now have 2 e to the u. So 2 e to the 2x. Evaluated from 0 to ln 2. Okay. So what's the value of this expression when x is ln 2? So 16 ln 2 minus 16 e to the ln 2 means 2. Property of logarithm, no? So this is times 2 plus 2 e to the 2 ln 2, that is equal to e to the ln 4, 2 squared, that is 4, and e to the ln 4 is simply 4 times 2, no? So yan. What about at the lower limit? So at the lower limit, 0 minus 16 times 1, e to the 0 is 1, and then plus 2 times e to the 0 is 1, so times 2. So we have 2. Okay. So getting what? Pi. So this is 16 ln 2. What about the remaining constants, guys? Guys. Oh, guys. Oh, guys. Y higher minus y lower. So that's the radius squared, no? Did I get correctly the expansion, guys? Okay. Hi, guys. Oh, you're not replying anymore, guys. Minus negative 16. Guys, compute please. Times 2 plus 8. This is negative 14, no? Plus 14. So that is negative 10. Am I correct? So what's the approximate value? So the volume is approximately, could you please check, guys, ha? A question, guys. Okay. Let's have this one, number 3. We have y is equal to sine x. And the x-axis, I want the area to be revolved, bounded by this, from, but I want it from x equals 0 to x equals pi over 2 only. Bounded by y equals sine x, and the x-axis from x equals 0 to x equals pi over 2. Axis of revolution, I want it to be, again, the, let's say, the x-axis, no? That is the line y equals 0. The x-axis, the line y equals 0. Okay? So, solution. I think we can go directly to the graph because this is sine. And you should know how to graph the sine function by this time, no? Especially if you're ECE, because you will be dealing with mga sinusoidal behavior. So if this is 1, this is something pi over 2. Let's say this is pi over 2. So I want it here. Yan. From there, no? Oh, this is the graph of the sine function. Okay. If you continue the sine function, it will go down here. And then to the left, it will be like this, no? Yan. Okay? But I want only 0 to pi over 2. So up to this only. Up to this point. Okay, guys? So, and then here. And then, of course, bounded by the x-axis. Yan. So that's the region. Yan. If I'm going to revolve that about this line, so this is what I will be able to generate. Yeah. So from here, this is my pi over 2. Let's say this is pi over 2. This is the y equals 1, where they will meet. So this is the curve. Okay, that's the curve. And we are going to revolve this region. Ito yung reflection niya. Here is the reflection. Meaning this is -1, the reflection. Okay. So this is the shape. Okay. Do you see that? Guys, can you imagine now the shape? We want circular disc if possible, no? To be circular disc, the element should be what? Should be perpendicular. And that is vertical, the appropriate one. So when you rotate that, let me rotate that here. It will form what? The disc, no? Okay. So this is the disc that is formed. Okay? Yeah. So what's the volume, guys? Using circular disc method, making use of vertical element. Secretario. Oh, what's the formula again, Secretario? Secretario. Pi. Secretario. Integral from A to B, r squared dt. Gonzales. Oh, what is our radius, Gonzales? Y higher minus y lower, right? What is our y higher? Y equals sine x. Y lower happens to be 0. So we don't need that anymore, no? Okay, so this is 0. So we have just sine x. Our dt is what? Dx, okay? Because this is vertical. Pi. Dominic T, what are the limits? From x equals what? 0 to pi over 2. Hi, guys. They are not anymore talking. Sine our radius, square it, then dt is dx. Okay? How do we evaluate this, guys? We can evaluate this using trigonometric transformation. This is even case. We have pi integral from 0 to pi over 2. The transformation here is 1 minus cosine 2x all over 2 dx. Okay? So that is equal to pi over 2 times the integral of 1 dx is x minus the integral of cosine 2x is 1/2 sine 2x evaluated from 0 to pi over 2. Okay? So this is equal to pi over 2 times the value of x minus 1/2 sine 2x when x is pi over 2 is pi over 2 minus 1/2 sine of 2 times pi over 2 is pi. So we have 1/2 sine pi minus the value of x minus 1/2 sine 2x when x is 0. So that is 0 minus 1/2 of sine 0. Okay? But sine pi is equal to 0. Sine 0 is also 0, giving pi squared over 4. So this is the volume of this solid generated by revolving this region about the x-axis. So pi squared over 4 cubic units. Another way to evaluate this integral is by using Wallis formula. By Wallis formula, we have volume is equal to pi integral from 0 to pi over 2 sine squared x dx. And this is equal to pi times, so here we have in the numerator 1 over 2 times pi over 2. So giving pi squared over 4 cubic units. We get the same answer. Okay?